The day is done now. The world around you is beginning to quiet. The windows are dark, the blankets are warm, and the distant hum of the universe is softer than usual. Tonight, you've found a gentle corner in the cosmos where nothing is urgent and everything drifts, so breathe slowly. Let your eyes get heavy. There is nowhere else you need to be except right here. Tonight, we're going to let go of the day by gliding into the strange beauty of something most of us have heard about but few have fully understood, the speed of light. But don't worry, you won't need equations or textbooks here, just a little curiosity and a soft willingness to wonder. Because light isn't just a flash or a beam, it's a secret thread that ties space to time, like a silent rhythm guiding the heartbeat of the universe. Before we start, tell me something small. Where in the world are you listening from? And what time is it for you right now? Just write it down below. It helps you feel part of something. A shared constellation of sleepy minds scattered across different countries and time zones, all lying back and drifting into the same calm sky. We may not see each other, but we're looking at the same light. So, the speed of light. It sounds like a superlative, like the punchline of a science fact. But what does it really mean to say that light moves at a speed, and more than that this speed is somehow special? Imagine this. A beam of sunlight leaves the surface of the sun and races through the vacuum of space toward Earth. That journey takes about 8 minutes, just 8 minutes. You could boil an egg in that time. You could walk to the corner store and back. But for a photon, a single particle of light, that's all the time it takes to cross nearly 150 million kilometers. That number, 300,000 kilometers per second, is dazzling, but also a bit abstract. What makes it more than trivia is this. No matter where you are in the universe, no matter how fast you're moving, the speed of light in a vacuum is the same. Always. For everyone. But how is that possible? If you're riding on a train and throw a ball forward, the ball's speed adds to the train's speed. That's what we expect. But with light, the rules change. If you're chasing a beam of light at nearly the speed it travels, you might expect the light to slow down relative to you. But it doesn't. It still zips ahead of you at the exact same speed. It doesn't care how fast you're going. It always stays light speed. Why? Why would the universe behave that way? To keep the speed of light constant, nature has to give up something else. It turns out what gets bent and twisted isn't light, it's time itself. Picture this. You're standing on a platform watching a train go by. On board, someone has set up a simple clock, just a beam of light bouncing between two mirrors. Tick, tock, tick, tock. Inside the train, the light goes straight up and down. But to you outside watching the train rush past, that same light beam traces a longer diagonal path as the train moves forward. The light travels more distance for each tick, but its speed hasn't changed. So what does that mean? It means the ticks are farther apart. Time is moving slower for the person on the train, at least from your perspective. That's not science fiction. That's special relativity. If the speed of light is always the same, time has to be flexible. It has to stretch or shrink depending on how fast something is moving. We call this time dilation, and it's not just a theory scribbled on blackboards. It's real. GPS satellites circling above the Earth tick at a slightly different pace than clocks on the ground. If we didn't account for that difference, your navigation app would be miles off. So light, by refusing to adjust its speed, forces time to do the adjusting instead. But this strange relationship has limits. You can never quite reach the speed of light if you have mass. The closer you get, the harder it becomes to go faster. Your mass effectively increases, the energy required shoots toward infinity, and time slows more and more. At the speed of light itself, time would stop entirely. But what does it even mean for time to stop? What would you experience if your clock no longer ticked? Here's where it gets stranger still. Light doesn't experience time. It doesn't age. From the moment a photon is emitted, from a star, a firefly, a flashlight, to the moment it strikes your eye, it travels without experiencing any passage of time. From the photon's point of view, its departure and arrival are instantaneous. There's no journey, just origin and destination fused into one event. But we don't live at the speed of light. We experience time. We feel it drift. We measure it with watches and yawns and growing older. For us, the photon's trip takes time. Seconds, minutes, even billions of years. It's this dissonance, it's this disconnect between how light moves and how we move that reveals something essential. Light acts as a kind of boundary, a limit baked into the fabric of reality. It's not just a speed, it's a cosmic law, a silent contract signed by every atom, every clock, every spinning planet. So the next time you see a sunbeam sliding across the floor or the flicker of a star from a distant galaxy, remember that light is more than illumination. It's a measure, a signal, a thread connecting places and moments. And still, a question drifts. If light always moves at this perfect, unchanging speed, what happens when something tries to move faster? Nothing we know of in the universe has ever succeeded in overtaking light. We've built particle accelerators that sling subatomic fragments to within a whisper of light speed, but never beyond. The closer these particles get, the more stubborn the universe becomes. The energy we pour in doesn't just make them go faster. It adds to their mass, subtly and then enormously, like trying to push a mountain through honey. At near light speeds, time stretches, mass inflates, and distance compresses. But the speed of light remains just out of reach, a horizon that recedes but never yields. And why is that? Why does the universe so fiercely defend this limit? To begin to understand, we have to step back from the chase and consider what this limit preserves. Imagine if you could exceed it, if something could move faster than light. Suddenly, cause and effect lose their order. A message could arrive before it was sent. A traveler might return home before they ever left. And while those ideas sound like clever puzzles, they erode the logic that reality depends on. Without cause preceding effect, nothing holds together. Light's speed isn't just a cap on motion. It's a safeguard for consistency. It's the invisible scaffolding that keeps time from unraveling. But does that mean light is the fastest thing in existence, or just the fastest thing allowed? Could there be something hidden that dances past this barrier, unknown to us? Theoretical particles like tachyons, imaginary entities that always move faster than light, have been speculated about but never seen. They remain ghosts of equations, unanchored to anything real. Every test we've run, every observation we've made, continues to reinforce the same strange truth. Light is the limit, and reality seems built to honor it. Let's imagine again. Picture yourself in a spacecraft, sleek and silent, steadily increasing in speed. As you go faster, your perception of the world outside begins to distort. The stars ahead of you shift toward blue, their light compressed by your motion. Behind you, they stretch toward red, losing energy, fading. Space begins to flatten in your direction of travel. The very distance in front of you shrinks, but inside the ship, you feel normal. Your heart still beats, your breath still flows, and your thoughts unfold in their usual rhythm. It's only from the outside, from a stationary observer, that things have changed. To them, your time has slowed, your mass has increased, your journey has bent the rules of what's familiar. But for you, time marches on, unaware of its own dilation. This strange duality, that time can behave differently for different observers, yet always makes sense to each of them, is not a trick. It's the architecture of space-time itself. And this architecture doesn't just emerge from the speed of light, it orbits around it. In fact, the very idea of time as a measurable, consistent experience only holds together because light behaves as it does. Now take that light clock again, the one with mirrors and a bouncing beam, and imagine it being carried aboard a spaceship, moving very quickly. To the person inside, the light bounces up and down, as always. But to someone outside, watching the ship fly past, the light travels on a diagonal, a longer path. Since the speed of light cannot change, and since the path is longer from the outside view, the only thing that can adjust is time. The ticks of the clock must come more slowly. This realization leads to something astonishing. Time is not universal. It's not a single ticking metronome that echoes through the cosmos. It's a local experience, personal and relative. Your time is yours. Someone else's time, if they're moving or farther from gravity's pull, can run at a different pace. That's not just theory. It's something we've measured. Atomic clocks flown on aircraft show it. Satellites use it to adjust their internal systems. And it all traces back to that unflinching loyalty the universe shows to light's speed. So what is light then? Is it just an electromagnetic wave, as physics describes it? A self-sustaining oscillation of electric and magnetic fields? Or is it something deeper, a principle, a symmetry, a law that whispers its presence into every corner of the cosmos? It turns out light is both a thing and a boundary. It has properties we can measure, wavelengths, energies, frequencies, and it also serves as a sort of ruler, an anchor for what is allowed. And yet, light itself doesn't appear to age. It doesn't experience time. It moves through space and emerges from stars and lasers and your phone screen, but from its own frame, if it even has one, the interval between departure and arrival is zero. For a photon, there is no journey, only two events, emission and absorption, with nothing in between. But can we even talk about a photon's frame of reference? That's the crux. The mathematics of relativity refuse to allow such a frame. Light always moves at the same speed in all frames of reference, which means it never stops anywhere long enough to have one. From our perspective, we can say it travels. But from its own, there is no passage of time, no sense of movement, and that realization is more than a curiosity. It tells us that light doesn't just reveal the world, it defines how the world can be revealed. Every image you've ever seen, Every corner of the night sky, every memory of a sunrise, has arrived via photons that never experienced time. They were created and absorbed in an instant from their point of view, and yet they carried information across vast distances, sometimes across billions of years, so that you could see a glimpse of the past in your present. That is the quiet miracle of light. It's a traveler that never travels in time, a whisper that never ages, a pulse that never fades until it finds something to illuminate. And yet, if time stretches the faster we move, if space warps around speed, then what would we find if we kept accelerating? What would it feel like to near the speed of light, not in theory, but from inside that voyage? To imagine that journey is to step outside the bounds of ordinary life. We live so deeply rooted in a slow world where walking across a room takes seconds and crossing a city might take hours. Our speeds are pedestrian, our distances tame. But what if we let go of those limits? What if we climbed aboard a ship built not of metal and wires, but of thought and possibility, and let it gather speed faster and faster, brushing past the moon, swinging by the planets, slipping beyond the solar system like a pebble through still water? As your ship accelerates, strange things begin to happen. The stars ahead don't just twinkle, they smear into lines. Their light shifts toward the blue end of the spectrum, their energy packed tighter and tighter as you rush toward them. Behind you, the universe seems to stretch, pulling into red, then black as photons lose energy and slip from view. The shapes outside grow unfamiliar. Space seems to flatten. Forward becomes denser, more compressed, as if the very fabric of distance is bunching up before you. And time, always so reliable, starts to slip. A clock on Earth might tick 1 hour, but on board your ship, only minutes pass. The faster you move, the more pronounced the difference becomes. Time itself is no longer a universal backdrop. It becomes elastic, stretching between observers, each one tethered to their own reality. Now imagine this continues. You reach 90% of light speed, then 99, then 99.9. Each tiny increase demands more and more energy, disproportionate and absurd. And the side effects amplify. Time crawls, space compresses, mass grows heavy and immense. Eventually, you inch closer and closer to the limit, 99.999%. At this point, from your ship's point of view, the outside world moves in a kind of freeze frame. Millennia pass elsewhere, while your heartbeat continues at its usual rhythm. A single second for you could be centuries for someone far away. But no matter how fast you go, the speed of light always stays just beyond reach. You can approach it asymptotically, drawing nearer and nearer, but you'll never cross it. Why not? Because the laws that govern your existence, your mass, your energy, your structure, are built to operate beneath that threshold. To surpass light speed would be to leave behind the very conditions that define you. It's not a speed trap, it's a transformation point. Past that, reality changes flavor. Particles lose their identity. Time behaves differently. And we, bound as we are to clocks and rhythms and aging, cannot follow. So what would happen if you could defy all of this? If somehow you could break through the barrier, if you could step beyond light's pace and look back at the universe through different eyes. The speculation is wild and mostly theoretical. Some suggest you'd see the past and future blur, Others propose paradoxes, situations where you arrive before you've left, or witness events unfold out of sequence. And perhaps that's why the limit stands so firmly, to protect the consistency of cause and effect, to ensure that what happens has a reason and that the reason comes first. But even without exceeding light, there is a mystery in simply approaching it. As you near the speed of light, the universe changes shape around you, and that shift isn't just visual, it's deeply physical. The space you travel through gets shorter. Distances compress in your direction of motion. A galaxy that once seemed impossibly far might now lie within reach. This effect, called length contraction, doesn't just exist in thought experiments. It's something we've confirmed through the behavior of particles in accelerators. To us, they travel farther than they should before decaying, because from their perspective, the distance is shorter. Time dilation and length contraction aren't tricks. They're baked into the geometry of spacetime, the four-dimensional fabric in which we live, and they reveal something profound. Movement reshapes reality. There's no absolute frame, no cosmic reference point. Everything depends on your state of motion. If you move fast enough, even time and distance lose their fixed identities. But light remains untouched. No matter how fast you move, how far you go, how extreme the transformation, light always travels at the same speed. It doesn't slow down. It doesn't speed up. It simply is. And because of that, it serves as the ultimate measuring stick. Everything else, space, time, mass, energy, dances around it. It is the silent conductor of a very strange orchestra, and perhaps that's the reason it can act as such a faithful messenger, because it doesn't care where it's coming from or who's watching. Light carries information across the universe, revealing stars, galaxies, and echoes of beginnings. It moves across vast distances, but always at the same pace. You can trust it. Whether emitted by a candle or a supernova, its journey unfolds with perfect discipline. Even as time bends and matter shifts, light stays loyal to its speed. But now, if time can slow and distances can shrink with speed, we begin to wonder, are these effects connected only to motion? Or are there other forces in the universe that can stretch time? Does something else, something not related to velocity, have the power to warp the ticking of the cosmic clock? The answer arrives not through speed, but through mass, through gravity. Gravity, the quiet sculptor of the cosmos, does more than pull apples and anchor planets. It bends space, and where space bends, time follows. This isn't just poetry. It's measurable, and it's real. If you climb a mountain, time moves faster for you than it does in the valley below. Not enough to feel, but enough to register on a precise clock. That's not because your heart changes its pace, or because you think differently at altitude. It's because gravity, even Earth's gentle pull, stretches time like taffy. The deeper you are in a gravitational well, the slower your time flows compared to someone higher up. And if gravity can slow time, then places with intense gravity, like the surface of a neutron star or near the event horizon of a black hole, must warp time dramatically. Not in theory. In fact, a clock on the edge of a black hole would appear to freeze from the perspective of an outside observer. The closer it gets to the event horizon, the slower it ticks, until finally it seems to stop entirely, suspended forever at the brink. But to the clock itself, to anything falling alongside it, time continues normally. Moments pass, thoughts unfold, heartbeats continue, though they will never be seen from the outside. Two truths, coexisting, separated not by distance, but by warped time. This phenomenon, known as gravitational time dilation, adds another thread to the story. It tells us that time isn't just relative to motion, it's also relative to where you are. More specifically, to how deep you are inside a gravitational field. This means that time is personal not only in motion, but in position. The universe isn't ticking to a single rhythm. It's alive with an infinite orchestra, each clock playing its own variation depending on its journey and its surroundings. And yet again, light stands as the quiet referee. A photon emitted from the bottom of a gravitational well must climb to reach you. In doing so, it loses energy, not by slowing down, but by stretching. Its wavelength gets longer. Its color shifts toward the red. This redshift isn't a trick of the eye. It's a consequence of time flowing differently at different depths. Light tells us where time stretches. It doesn't just pass through these zones, it reports them. This is how we've come to know the universe, not by touching stars or visiting black holes, but by reading the messages carried on waves of light. Light from distant galaxies, from deep gravitational pits, from ancient explosions, each one shifted in color, stretched in wavelength, bent in path. And by understanding those changes, we can trace how time behaves elsewhere. Light becomes not just a speed, but a story, the silent courier of how space and time are intertwined. But gravitational time dilation doesn't require exotic objects. It's happening now. On Earth, clocks on the surface tick more slowly than those in orbit. That's part of why the satellites that run GPS systems need constant correction. Their clocks drift not only due to speed, but also because of gravity. Without adjusting for both effects, your phone's navigation would steer you astray. This is not science on the edge. This is science in your pocket. And still, the implications grow deeper. If time can stretch with speed and sag under gravity, what does that say about its nature? Is time a substance, something elastic that can be pulled and compressed? Or is it a dimension, like space, which can be curved and folded by mass and energy? According to Einstein's theory of general relativity, it's both. Space and time are not separate fabrics. They are woven together, inseparable, forming a single tapestry called spacetime. And that fabric isn't flat. It curves around mass, and in doing so, tells matter how to move. Mass tells space how to curve, and space tells mass how to move. A perfect loop. That's why light doesn't always travel in straight lines. When it passes near a massive object, its path bends. Not because the object is pulling on it like a magnet, but because the space it travels through is curved. The straightest possible path, what physicists call a geodesic, is no longer a straight line in our traditional sense. It's the natural curve of a warped world. And since light always travels along these geodesics, its path becomes a map of the curvature around it. Follow the path of a photon, and you trace the shape of space. This bending of light was first confirmed during a solar eclipse in 1919 when starlight was observed to curve around the sun. The stars appeared displaced, not because they moved, but because their light had taken a curved route to reach Earth. That single observation transformed Einstein from a theoretical physicist to a household name. But more importantly, it confirmed that gravity affects not just matter, but light, and therefore time itself. So now we find ourselves with a richer view. Time is not absolute. It flows differently depending on how fast you move and how deep you stand in a gravitational field. And light is both messenger and mapmaker, revealing the hidden geometry of the cosmos. It carries more than energy, it carries structure, and in this strange, bending, layered universe, one begins to wonder if time can move at different speeds and space can bend like cloth. Is there a place where time might stop altogether? If time can slow, bend, and stretch, then it seems natural to ask where it might come to a complete halt. The answer, once again, leads us to the edge of gravity's dominion, to the mouth of a black hole. Not just any region in space, but one where gravity becomes so intense, so concentrated, that escape becomes impossible. Not even light, the swiftest traveler in the universe, can break free. And it's here, at the boundary called the event horizon, that time appears to freeze from the outside's perspective. If you were to watch an object fall toward a black hole, you would never see it cross the horizon. Instead, it would seem to hover, slower and slower, dimmer and redder, until it faded from sight, not because it vanished, but because time itself stopped moving forward in your frame of reference. But from the object's own point of view, if it could feel or think as it plunged, there's no sensation of freezing. It continues past the horizon, crosses that boundary as if it were any other point in space. Time flows for it just as before, uninterrupted. So which is it? Has time stopped or not? This contradiction only exists if we assume time is absolute, but it isn't. Time is relative, and each observer carries their own clock. What feels like an ending to one might feel like a continuation to another. This is where things begin to blur, not just physically, but philosophically. When we speak of time halting, we have to specify to whom, from where. Because in the realm shaped by relativity, no event has a single, universal timestamp. There's no cosmic clock ticking in the background, no divine metronome governing the universe. Instead, each particle, each observer, each traveler experiences time in their own frame, bound by their speed and their gravitational environment. It's unsettling in a way. We're so used to time as a shared thread, birthdays, sunsets, the rhythm of a familiar song. We assume the world is synchronized, but on a cosmic scale, there's no such thing. A second for you might be different from a second for someone else. The universe keeps no master schedule, and yet somehow it all fits together. The contradictions dissolve when we allow for a more fluid model, not of time as a marching line, but of time as a flowing river with eddies, currents, and still pools. In that model, light is the bridge between these differing experiences. Because it always travels at the same speed, it provides the invariant structure that lets us compare one clock to another. Light carries the differences, encodes the delays, shifts, and curves. It lets us see into other frames. A photon leaving the surface of a neutron star tells us how slow time runs there. A beam from a speeding satellite reveals how motion stretches time. Without light, we'd be blind not just visually, but conceptually, unable to trace the shape of time itself. And yet, even light has limits. Around a black hole, its path bends into loops. If you stood just outside the event horizon and released a beam of light sideways, it could orbit the black hole in a perfect circle, forever trapped, never falling in, never escaping. This is the photon sphere, a fragile, unstable halo where light itself is tethered by gravity's grip. Any closer, and even light falls inward, never to return. Any farther, and it escapes, though not without a struggle. At the horizon itself, escape velocity equals the speed of light. Nothing with mass can reach it. Light alone defines the edge, and that edge isn't a wall or a surface. It's a threshold in space-time, a place beyond which all future paths point inward. To cross it is to commit to a fate unseen, unreturnable. But for light, time doesn't pass in the usual sense. From its own perspective, if such a thing exists, the fall into the black hole is instantaneous. And so, we're left with paradoxes stacked upon paradoxes, where time stops from afar but continues up close, where light traces paths through curved space, yet never experiences those paths itself. It's almost too strange to believe. And yet, every prediction, every equation, every measurement agrees. The universe is not flat and fixed. It is a living structure, shaped by gravity and motion, and navigated by light. And so we begin to see the speed of light not as a barrier, but as a blueprint, the thing that defines the limits of space and time. It's what ensures order, prevents chaos, and preserves causality. And perhaps most astonishing of all is this. Despite the immense distances and terrifying densities, despite the warping of time and the collapse of meaning near black holes, light still tells the story. We can't see inside an event horizon, but we can see its effects on light near the edge. We can trace how it distorts starlight, creates gravitational lensing, warps entire galaxies behind it. We can observe its signature, written in bent photons and redshifted echoes. Light reveals what even time seeks to hide. So in a universe where time is relative and gravity curves its flow, we rely on light, steady, unwavering, to show us the shape of things. It moves through a world of shifting hours and folding distances, and always at the same pace. But if all of this, the warping of time, the bending of space, the stability of light's speed, is real and measurable, then how does it all fit together? Is there a deeper framework that explains why light plays this role? Is there a geometry beneath it all, waiting to be seen? There is a framework, and it begins with the notion that space and time are not separate, independent entities. For centuries, we treated them as distinct, space as the vast three-dimensional stage upon which matter moved, and time as the silent ticking that marked each moment of that motion. But Einstein's insight, the one that quietly rewrote the architecture of reality, was that space and time are woven together into a single continuum, space-time. Not a metaphor, not a clever diagram, but a real physical entity, curved, elastic, and dynamic. And the warp and weft of that fabric define everything we experience, from falling apples to orbiting planets to the flow of time itself. So how does light fit into this new geometry? To understand that, imagine space-time as a flexible sheet. If the sheet is flat, light travels in straight lines. But if mass is placed upon it, a star, a planet, anything with gravity, the sheet dips. Light must follow the shape of the sheet, bending along with the curve. But more than that, the dip isn't just a curvature in space. It's a curvature in time as well. The more mass, the deeper the dip, the slower time flows at that location. What we perceive as the force of gravity is really just objects following the natural curves of spacetime, geodesics, the straightest possible paths in a bent universe. And light, always obedient to those geodesics, becomes our tracer. It sketches the contours of the sheet. Its paths, when bent or delayed, reveal the depth of the dips. In gravitational lensing, where the light from a distant star or galaxy is distorted by a massive object in the foreground, we witness space-time itself acting like a lens. The foreground mass bends the fabric, and light obeys, curving along its surface. We don't just see the distant light, we see its history, its path through the invisible warps of the cosmos. This idea that the presence of mass tells space-time how to curve, and the curvature of space-time tells mass how to move, is the core of general relativity. And it's here that the speed of light takes on an even more profound role. It's not just a maximum speed, it's the ratio that connects space and time, the very conversion factor that defines the slope of those geodesics. In the mathematics of relativity, the speed of light links distances with durations. It's the tilt in the fabric, the angle of time's flow through space. Consider this. In a light clock, where photons bounce between mirrors, the speed of light determines how long each tick takes. If the mirrors move, the beam travels diagonally, taking a longer path. But the speed cannot change, only time can adjust. That's not just an illusion or a side effect, it's a geometric necessity. The constancy of light's speed constrains the structure of spacetime. It sets the rules by which clocks must tick and rulers must stretch. If light moved differently for different observers, the entire coherence of reality would collapse. Events wouldn't agree, histories wouldn't align, causality would crack. So in a way, light doesn't just move through space-time, it defines it. It is the measure by which all other measures are compared. And because of that, the speed of light is not simply a speed. It's a feature of the universe's very fabric, a number that arises from how space and time intertwine. This becomes even clearer when we consider the concept of simultaneity. In our daily lives, it feels obvious that two things can happen at the same time: a flash of lightning and a clap of thunder, or two clocks striking midnight on opposite sides of a city. But in the realm of relativity, simultaneity is slippery. Two events that appear simultaneous to one observer may not appear so to another, moving at a different speed. There is no absolute now that everyone agrees on. This isn't just a philosophical wrinkle, it's a direct consequence of the speed of light. Because light takes time to reach us, and because that time is different depending on motion and position, our perception of when is forever filtered through the paths that light takes. That means our sense of present is inherently local, defined by where we are and how fast we're moving. The idea of a universal moment shared across the cosmos simply doesn't exist. Light's finite speed denies us that privilege, and yet there's a quiet beauty in this. It means that every point in the universe has its own rhythm, its own sense of time, and light, traveling steadily through all of it, knits those rhythms together. It is the silent courier, carrying news from distant places and ancient moments, binding scattered nows into a comprehensible whole. So when you gaze at a star, you aren't just seeing something far away, you're seeing something long ago. That light left its source years, decades, even millennia ago. It traveled through the vacuum, untouched, until it finally entered your eye. And because it traveled at light speed, it experienced no time at all. From the star's surface to your retina, it crossed not just space, but history. And yet to the photon, the 2 points were adjacent, almost indistinguishable. In that way, light reveals the past without aging. It connects events that are separated by distance and time, stitching the universe into a shared tapestry of visibility. Every beam is a message from a different when and a different where, and we, here on Earth, are constantly bathed in those messages, the glowing language of the cosmos. But the deeper we explore, the more this connection between light and time reveals its limits. There are places, even now, where light has not yet reached us. Distances so vast and timescales so immense that the earliest photons from those regions are still on their way. That leads to a sobering thought. The observable universe is not the whole universe. It is just the part that light has had time to reach. Everything beyond that horizon remains unseen, not because it is hidden, but because its light has not yet arrived. So then we ask, if light defines what we can see, does it also define what we can know? In a profound sense, yes. Light draws the boundary between what is visible and what is unknowable. Everything we've learned about the universe beyond our planet, beyond our solar system, has come to us through light. Not just visible light, but radio waves, microwaves, X-rays, gamma rays, all part of the same spectrum, all moving at the same speed, all telling stories from across the cosmic sea. We read those signals the way sailors once read the stars, carefully, patiently, with reverence. Light carries fingerprints of atoms, the wobble of planets, the recoil of distant galaxies. But it cannot deliver what it has not yet had time to cross. This defines the concept of the observable universe, the region of space from which light has had enough time since the beginning to reach us. It's a quiet boundary, not a wall, but a horizon, the cosmic light horizon. Beyond it, the universe may continue endlessly. There may be galaxies, clusters, entire structures we will never see, not because they don't exist, but because their light, moving at its absolute unwavering speed, hasn't reached us yet, or perhaps never will. Because the universe is not static, it's expanding, and it's doing so not just rapidly, but accelerating. The very fabric of space is stretching, pulling distant objects away from us faster and faster. Some galaxies are already moving away at such a rate that their light, though traveling at light speed, can never catch up. The space between us and them stretches faster than the light can bridge, and so we encounter a strange fate. Every day, the observable universe shrinks in a deeper sense, not in size, but in access. The light we see now from some galaxies may be the last we ever receive. In time, they will slip beyond reach, their signals redshifted into oblivion, their light stretched into silence. In the far future, all but the closest galaxies may fade from view entirely. The night sky will grow darker, not because stars have died, but because light can no longer arrive. The universe will still be full, but we will be alone in the dark. This idea that knowledge is bounded by light is both humbling and oddly comforting. It reminds us that the universe is vast, dynamic, alive in ways we may never fully grasp. But it also deepens our appreciation for every photon that does arrive. Every ray of starlight, every whisper from a quasar, every delicate pulse from a pulsar is a triumph over distance and time. A gift delivered with perfect consistency, unchanged in speed since its departure, undeterred by eons. Light does not stop, it simply goes, and in its going, it reveals. But what does it mean then to say that light is timeless? We've said that photons don't experience time, that from their perspective, there is no journey. This conclusion arises from the equations of relativity. A photon traveling at light speed has no time in its own frame. But here we meet the edges of our understanding, because if a frame of reference requires a clock and a photon has no time to tick, then perhaps it cannot even possess a frame of reference in the usual sense. We can describe its motion from our perspective, but not its experience, because it has none. It exists only in interaction, the moment it's created and the moment it's absorbed. The in-between is not its story, it is ours. Still, those two moments, creation and absorption, are stitched together across incomprehensible gulfs. Light links past to present, distant to near, in an instant that stretches billions of years for us. It's a bridge that spans not just space, but epochs. The light we see tonight from a star in Andromeda left before humans discovered fire, and yet, when it reaches your eye, it does so instantly from its own non-existent perspective. It traveled for 2.5 million years, and yet it did not wait. This paradox doesn't demand solving, it demands marveling, and perhaps that's why light fascinates us so deeply. It behaves like a wave, yet arrives like a particle. It moves at the universe's maximum speed, yet does so with no experience of motion. It defines causality while carrying the past into the present, and it allows us, tiny creatures on a small planet, to understand things that happened before we existed, in places we will never touch. So we build telescopes, detectors, sensors that stretch our reach beyond the visible. We capture ancient light, decode its patterns, infer the mass and motion and chemical makeup of objects unimaginably far away. We map galaxies, detect supernovas, trace the fingerprints of gravity in the way light bends, and still we find more light, always more light, waiting in the dark. One of the most astonishing examples of this comes from a place even older than stars, the early universe itself. Just a few 100,000 years after the Big Bang, light was finally free to move. Before that moment, the universe was a dense, hot plasma, opaque and roiling, where photons couldn't travel more than a few millimeters before scattering. But as the universe expanded and cooled, it reached a threshold. Atoms formed, the fog lifted, and the first light was released, free to travel through space, uninterrupted. That ancient light, the cosmic microwave background, still exists. It fills the universe like a whisper from its earliest breath, and we can see it. We build instruments so sensitive they can detect those primordial photons, stretched now into microwaves by the expansion of space. They paint a picture not of stars, but of the universe's birth pangs. Tiny fluctuations in temperature, denser patches where galaxies would someday grow, fainter spots where emptiness would stretch. That light tells us the age of the universe, its shape, its content. It is our deepest history, and yet, like all light, it traveled without time, arriving in our detectors not as a relic, but as a messenger. And still the question floats. If this is the light from the beginning, what came before? Before that first light escaped into the vastness, before photons could roam freely through space, the universe was cloaked in opacity. It was hot, dense, and young, unimaginably young, less than 400,000 years old, a mere blink in cosmic time. In that early era, the universe was a plasma sea, so dense with charged particles that light was trapped in a constant dance of collisions. Photons would scatter off electrons again and again, unable to move more than a fraction of a centimeter without being redirected. It was a glowing fog, not with beams or rays, but with the blinding uniformity of light that couldn't travel freely. And so, though the universe existed, it was blind, not because light wasn't present, but because it could not yet carry information. There were no shadows, no stars, no structure, only motion, heat, and waiting. But as the universe expanded, it cooled. Slowly, incrementally, the furious energy of those first moments faded, allowing the chaotic particles to settle. Electrons found protons, forming neutral hydrogen atoms. And in that quiet chemical shift, something miraculous happened. Light was finally free. Photons, no longer interrupted by electric charges, began to travel great distances unhindered. They streamed outward in every direction, carrying with them the imprint of that first moment of clarity, the memory of a universe made suddenly visible. That light still exists. It hasn't faded. It's stretched, cooled, and dimmed, but it continues to arrive, every moment from every direction. We call it the cosmic microwave background, but it's more than background. It's the floor beneath all starlight, the first note in the long song of illumination. What's extraordinary is that this light gives us a picture of the universe, not as it is now, but as it was then, in its infancy. A smooth field of energy, peppered with slight irregularities, tiny ripples in density that would later grow into galaxies, clusters, voids. By studying this ancient light, we can read the conditions of the early universe with astonishing precision. We can tell how much matter there was, how much dark matter, even how fast the universe was expanding. The pattern of those ripples acts like a cosmic fingerprint, and we've become expert at reading it. But this birth of light wasn't just a milestone in the universe's history. It was also the beginning of cosmic memory. Before this moment, information was locked inside the fog. After it, light could carry stories across time. The universe, in a sense, became capable of remembering itself, and it chose light as its medium. It's tempting to think of light as illumination, something that reveals. But this light, this first light, did not reveal anything in the moment. There were no eyes to see it, no surfaces to reflect it, no structures to cast shadows. It simply began to travel, and in doing so, it preserved a record. It carried forward a map of temperature variations, of density, of structure waiting to unfold. Billions of years later, we would build machines to detect it, to decode its subtle variations, to listen to its quiet hum. And in doing so, we would see farther back in time than ever before, not with our eyes, but with instruments tuned to the most ancient whisper of all. This raises an interesting point. How far back can light take us? We've said that the cosmic microwave background marks the beginning of visibility, the first photons to travel freely. But beyond that, before that, lies a deeper fog, one no light can penetrate. a time so hot, so dense, that photons were permanently tangled in collisions. And beyond even that, there was a period so close to the origin, so alien to our current physics, that we don't yet know how to describe it. This is the limit of electromagnetic observation. Light can take us far, but not to the very beginning. For that, we would need a different kind of messenger, gravitational waves perhaps, or some yet unknown phenomenon that can travel through the earliest chaos. But even then, the principle remains the same: motion through space-time, constrained by the cosmic speed limit, bringing news from the edge of the unknown. And that speed, the speed of light, continues to define what is accessible and what is out of reach. Not just spatially, but temporally. Because of it, looking far into space is looking back in time. A galaxy 10 billion light years away is not just far, it is 10 billion years ago. The light we see from it, left before the Earth formed, before the sun began to shine. In that sense, astronomy is not a study of space, but a study of the past. Telescopes are time machines, and photons are the messages they receive. We don't look out, we look back. This idea bends our perception. We live in the present, but we see the past. Even the moon, serene and constant, reflects light that left it over a second ago. The sun, bright and life-giving, sends light that departed 8 minutes before. The starlight we wish upon may have left its origin before our ancestors stood upright. And yet, when it arrives, it feels immediate, a twinkle, a glimmer, a presence. Light is the past delivered into the present, so seamlessly that we rarely notice the delay. And all of this hinges on one fact: light travels at a finite speed. If it were infinite, everything would be simultaneous. We'd see the universe as it is, not as it was. Time would collapse into a single, frozen moment, but it doesn't. Instead, the slowness of light, not slow in any human sense, but slow compared to infinite speed, gifts us with a sequence, a layering of events. It turns the sky into a storybook where every point of light is a different page from a different chapter, all glowing at once. And this leads us to a profound realization. The arrow of time, that one-way flow we all experience, is deeply connected to the way light behaves. Light only goes forward. It moves outward from events, never inward. We don't see light from the future. We don't receive beams from things that have not yet happened. And so, one must ask, is light itself part of what defines the flow of time? That question touches something elemental, something that slips beneath equations and technical descriptions into the fabric of experience. We feel time moving. We wake, we age, we remember. Always forward, never in reverse. And yet, the laws of physics, most of them at least, do not require this. They allow time to flow either way. The equations are symmetric. A falling object, a swinging pendulum, a colliding particle, all of these processes look just as valid when played backward. But we do not see time reverse. We do not experience a coffee cup unbreaking or the warmth of a fire returning into the logs. Why? The answer seems to lie not in the mechanics of physics, but in the subtle realm of entropy, the measure of disorder. Over time, entropy increases. Systems move from order to chaos, from concentrated energy to diffuse energy. It is this gradient, this irreversible spreading out, that gives time its direction. Not because the fundamental particles care, but because the collection of them together, settles into statistical patterns that cannot be undone without effort. And light, though seemingly passive, plays a role in this process. It carries energy away. It radiates heat. It smooths out temperature differences. A hot object glows, loses energy, and cools. But it never spontaneously reheats by absorbing scattered light from its surroundings. Light flows outward. It disperses, not reverses. It marks the passage of time, not with a clock's tick, but with its own spreading presence. Every moment in which light leaves an object, a candle, a body, a planet, is a moment of entropy increasing. Photons radiate outward, thinning as they go, painting the past into the fabric of space. Once gone, they do not return. The information they carry may still exist, in theory, on the wavefront expanding ever outward. But in practice, those photons drift beyond retrieval. The moment is lost, not forgotten, but ungraspable. This is the arrow of time, not a force, not a law, but a direction traced by light and entropies alike. It tells us what can be remembered, what can be predicted. You can remember the past because the light from those moments has reached you, but you cannot remember the future because its light has not yet arrived. Vision itself depends on this. You do not see objects. You see the light they emitted or reflected a moment ago. You do not hear events. You hear their vibrations delayed by the finite speed of sound. Experience is always an echo, a delayed reflection of what was. And this delay is not just inconvenience, it is structure. Without it, we would lose sequence, story, memory. The universe would blur. Instead, light's steady pace, fast enough to link worlds, but slow enough to preserve order, gives us history. And that history becomes the bedrock of meaning, not just in science, but in life. We know things because light has told us. We infer, we deduce, we wonder, all because a photon left somewhere, traveled, and arrived. In this sense, light is not only a carrier of information, it is a constraint on information. You cannot know what happens in a place until light has had time to bring you the news. This delay enforces causality. You cannot act on something you have not yet observed. You cannot respond to an event before its light reaches you. This temporal structure builds reality as we know it, a web of connected events, each bounded by the speed at which information travels. But what about places where even light cannot escape? In black holes, again, we reach a boundary. Inside the event horizon, no signals can exit. That doesn't just make them invisible, it makes them causally disconnected. Nothing inside can affect the outside. From the universe's point of view, those regions are sealed. Their internal futures, whatever they may be, cannot influence the rest of reality. The flow of time continues within, but without light escaping, that flow becomes irrelevant to us. It's as though a section of the story has been torn out, existing still, but unreadable. This shows us something important. Light doesn't just illuminate space, it connects time. It threads moments together, creating lines of causality. You could imagine a diagram of the universe, with space plotted on one axis and time on another. A light signal would trace a straight diagonal line through this diagram, the steepest slope allowed. Nothing can cross that line going faster. That line becomes a kind of boundary, the outer edge of what can influence what. This kind of diagram is known in physics as a light cone. Every event has one. The cone opens outward into the future, bounded by the paths light could take from that point. Anything inside the cone is a possible effect. Anything outside is unreachable. It lies in the elsewhere, unable to be affected or to affect. The light cone shapes causality, defines potential, limits knowledge. And just as each event has a future light cone, it also has a past one, a region of space-time from which light could have reached the event. Your birth, your thoughts, your breath, all sit at the intersection of past light cones. The warmth of the sun, the breeze that touches your skin, the voice of someone far away, all are signals arriving from their respective pasts. The present is a meeting of histories, a tangle of light cones converging on your now. It's beautiful, then, to realize that every instant is not just a location in time, but a culmination of journeys. Photons arriving from countless sources, from places near and far, from events old and new, all entering your eye, your world, your moment. And they do so within strict limits, never faster than the speed of light, never backward in time, always obeying the rules that stitch the universe together. So when we say the speed of light is constant, we are saying more than a number. We are describing the speed at which reality knits itself. We are naming the pulse of connection, the breath of understanding. Every time we see, we are witnessing the universe arriving at the only speed it allows. But still we wonder, if the universe is expanding and the speed of light never changes, what happens to the light from the most distant stars? Does it ever reach us, or is it stretched so thin that it fades into nothing? It does reach us, sometimes, but not always. The expansion of the universe adds a twist to the story of light. Imagine space not as a rigid grid, but as a flexible fabric that stretches over time. Now picture a photon traveling through that space, racing steadily along its path. As the space expands beneath it, the distance it must cover increases even while it moves. This means that although the photon never slows down, it always travels at light speed. The ground beneath it pulls away, like a conveyor belt extending faster than a runner can cross. This is the peculiar condition of a universe not just large, but growing. So, light from distant stars does travel toward us. But if the expansion between us and the source is fast enough and accelerating as we now know it is, then the light may never arrive. Not because it was never sent, not because it's too far, but because the space between is expanding so rapidly that the photon's progress is forever outpaced. It's like a message in a bottle tossed into a river that widens faster than the current flows. The bottle doesn't stop, it just never reaches the other side. This is why there's a limit to what we can observe. There's a horizon, not defined by walls, but by time and expansion, a boundary beyond which light will never reach us. The observable universe, vast though it may be, is only a portion of the whole. There are stars, galaxies, perhaps structures larger than any we know, that lie beyond that horizon, unrevealed not because they are distant in the traditional sense, but because their light, traveling faithfully at light speed, cannot overcome the stretching sea of space. And even for the light that does arrive, the expansion of space leaves a fingerprint. It stretches the wavelength of the photon, elongating it, draining its energy. A wave that might have begun in the ultraviolet arrives in the infrared, or even as microwave. This is the cosmological redshift. It's not a Doppler effect in the usual way, not just the result of a source moving away, but a deeper change. It's the effect of space itself expanding, of time's scaffold growing beneath the wave. The light becomes a thread stretched over an ever widening gap. This redshift tells us how far and how long light has traveled. It becomes a cosmic clock. The higher the redshift, the earlier the light was emitted, and the more the universe has expanded since that time. We use it to measure distance, but also to look back in time, to trace the timeline of structure, the birth of stars, the clustering of galaxies. In a sense, redshift is a record of the universe's breathing, each stretched photon a signature of expansion. And as space continues to expand, the most distant galaxies edge closer to the horizon. Some already lie beyond it, and more will follow. Their light is still arriving now, ancient photons set in motion billions of years ago, but one day that flow will end. The last photon from a distant galaxy will arrive, and then no more. The source will not have disappeared, but it will have faded beyond reach, as if slipping behind a curtain drawn by time itself. This paints a melancholic picture of the far future, a time when the universe grows dark, not because stars have ceased, but because their light no longer comes. The night sky, once rich with stories and signals, will quiet. Local galaxies will remain visible, bound together by gravity, but the greater web of cosmic connection will fade from view. The observable universe will shrink to a single island, isolated, quiet, alone. Yet in that quiet, the light that remains will still obey the same speed, the same law, the same gentle rhythm that has always shaped reality. The constancy of light's speed is not something the universe has grown out of. It's something it has grown with. It is the rule beneath all others, the baseline tempo of existence. And even when the stars are gone, the echoes of their light will still ripple through the expanding void, stretched, dimmed, but still loyal to the rule. There's a strange comfort in this. Even in a universe slipping into darkness, the laws hold. Light still travels, time still flows. The speed of light still defines the bridge between cause and effect, even as fewer travelers walk it. And perhaps it is this idea that light is the universal constant, the unchanging whisper in an evolving world, that makes it so profound, because from the beginning to the farthest possible future, light has not wavered. It emerged from the chaos of the early plasma. It slipped free in the era of recombination. It bent around galaxies and danced through dust. It entered our instruments and our eyes. And it did all of this without changing its pace. It allowed time to stretch, clocks to slow, distances to shrink, but it itself remained unchanged. And so, when we ask, what happens to light from the most distant stars? We are really asking what happens to connection, to vision, to the fabric that lets one place know another. The answer is that light endures as long as it can. It travels, it stretches, it fades, but it does not give up. And even when the expansion of space outpaces it, that limit only defines what can still be touched, not what still exists. We may never see those galaxies again, but we once did. Their light reached us. It filled our instruments and gave shape to our sky. And that alone gives them a kind of permanence, not of presence, but of impact. Their photons became part of our knowledge, part of our maps, part of the grand story. So then, with all this in mind, what does it mean to say that light is information? It means that every photon is a message, not a metaphorical message, not an artistic gesture, a literal transfer of information. A photon carries with it the properties of its source, its energy, its direction, its frequency, its polarization. From these, we can deduce temperature, motion, composition, distance. When you see a star's light, you are receiving data, raw, unfiltered, ancient. It tells you what the star is made of, how fast it's moving away, how hot its surface is, whether it's spinning, and even how old the light is. That tiny flicker across your eye is a cascade of details, encoded in the language of wavelength and amplitude. It's not just something pretty, it's knowledge traveling across time. We don't need to touch a star to understand it. We don't need to send a probe into a quasar to know its mass. We look at its light. We analyze the spectrum, the fine lines of color absorption where elements leave their marks. Hydrogen, helium, carbon, iron, each leaves a unique fingerprint. These spectral lines let us identify what's there, even when it's billions of light years away. It's like writing a barcode, except the barcodes are etched by the physics of atoms, and the scanner is every telescope pointed skyward. And the deeper we look, the older the information becomes. We look not just across space, but into the past. The most distant galaxies we observe are also the youngest, not because they haven't aged, but because their mature light hasn't yet arrived. The photons we see today were emitted when those galaxies were newly born. So we witness the adolescence of the cosmos while standing in its present. In a very real sense, astronomy is a science of echoes, an archaeology of light. But light doesn't just describe the visible, it tells us about the invisible too. Consider exoplanets, planets orbiting stars outside our solar system. They are too faint to see directly in most cases, and yet we can detect them. How? By noticing the slight dimming of a star's light as a planet passes in front of it, or by measuring the wobble in the star's light caused by the planet's gravitational tug. These tiny changes, often just a fraction of a percent in brightness, or a barely detectable shift in frequency, are enough. With careful measurement, we not only confirm the planet's presence, but we can estimate its mass, its orbit, even the composition of its atmosphere. From a single beam of starlight, we can learn whether it rains ammonia on a world we've never seen. Light delivers that. It becomes clear that light isn't merely something that allows us to see. It is the currency of communication across the universe. It is the only means by which we can know what happens in the vast, unreachable regions beyond our own. And it obeys strict rules. It doesn't lie. It carries what it's given. It can be distorted, absorbed, scattered, but not falsified. And because of that, it builds the foundation of trust in science. We trust the photons we catch. We build our models around them. We base our maps of the cosmos on their messages, and they haven't let us down. Even now, light is delivering news. Photons that left a supernova decades ago might be arriving tonight. A gamma ray burst from the other side of the universe may just now flash through our detectors. These events are spontaneous, unpredictable, but not silent. Light spreads their news. The universe, despite its emptiness, is full of signals, and we, fragile and tiny, have learned to listen. Sometimes, the information light carries is terrifying. A star collapsing into a black hole, a collisions of neutron stars, a galaxy being devoured. These are violent, catastrophic events. But the light they emit reaches us gently with no threat. It arrives as data, as knowledge, as quiet wonder. We do not suffer its energy. We absorb its meaning. Light transforms violence into story. And this applies not only to the grand events of deep space, but to the smallest ones here on Earth. When you look into someone's eyes, you are seeing light reflected from their retina. When you glance at a leaf, you are reading the absorbed and reflected photons shaped by chlorophyll. Your entire perception of the world, your sense of color, motion, depth, is based on photons hitting your body, your eyes, your skin. The warmth you feel on your face in the morning sun is the touch of photons that left the solar surface 8 minutes ago, flew unimpeded through millions of kilometers of space, and landed finally on you. The same laws, the same constants, the same speed. Whether it's the glow of a distant galaxy or the light bouncing off a window pane, the mechanism is the same. The physics is universal. That is the quiet unity of light. It connects the colossal to the mundane. The laws that govern the glow of a quasar are the same ones that let you read this page. The photons that let us study the universe also let you recognize a face, see a sunset, find your way in a darkened room. They are the same particles, the same waves, the same speed, always the same speed. And that constant speed, unyielding, unwavering, is what allows light to carry information reliably. It sets the scale for causality, the boundary for communication, the tempo of time. If light were slower, the universe would be different. Delay would shape everything. If it were faster, infinitely fast, information would arrive too quickly, all at once, crushing the concept of sequence, of past and future. The universe's clarity would dissolve into noise. The constancy of light's speed is not just a feature. It is the reason the universe can be known. But light doesn't last forever. It can be absorbed, scattered. It can fade into wavelengths so long they no longer interact. Given enough time and expansion, even light becomes background, a whisper on the edge of detectability. And so we ask, how far can light travel before it disappears into silence? It depends on what it encounters, how far it goes, and how much the universe changes along its path. In a perfectly empty vacuum, a photon could in principle travel forever. Nothing slows it, nothing drains it, nothing stops it. It would continue onward indefinitely, a silent line through expanding space, stretching farther and farther from its origin. But the universe is not perfectly empty. It contains particles, fields, dust, and the structure of space-time itself, all of which influence light's journey. Over great distances, even the most energetic photons may be absorbed, scattered, or redshifted into oblivion. So while light never tires, its clarity fades, not because it forgets, but because the universe mutes it over time. One of the most potent ways light is altered is through redshift. As the universe expands, space stretches, and with it, the wavelength of the photons traveling through it. Longer wavelengths mean lower energy, so a photon that began as visible light may arrive as infrared. A gamma ray may become a microwave. This stretching doesn't destroy the photon. It transforms it, pulling it into a quieter register of existence. And if the universe continues to expand, especially if it keeps accelerating, then light from today's brightest events will someday reach wavelengths so long that they no longer interact with matter in any meaningful way. They won't warm anything. They won't illuminate. They'll simply float, undetectable, like forgotten messages written in a language no one can read. That's one kind of disappearance, the fade into length. Another comes through interaction. As light travels, it may encounter gas, dust, or charged particles. These can absorb the photon or scatter it, changing its direction or its energy. In intergalactic space, this is rare. Most of it is empty enough for light to travel unhindered. But over billions of years, even tiny interactions accumulate. And there's the cosmic fog, the sea of background photons from the early universe. High-energy photons traveling through this background can collide with those ancient, low-energy particles. The result? Mutual destruction, converting both photons into something else. So even light from powerful sources, like distant blazars or quasars, may never reach us if its path takes it through too many obstacles. And then there's time, the sheer span of it. Given enough time, every photon, no matter how strong, will eventually be absorbed, scattered, redshifted, or diluted into insignificance. Not lost in the way a stone sinks into the ocean, but transformed, softened, pulled into the long tail of cosmic history. It's not that light vanishes, it becomes part of the background hum, the quiet that grows as the universe ages. In the far future, if the universe continues on its current trajectory, galaxies will fade from each other's view. The night sky, once crowded with stars and galaxies, will become increasingly empty. Only the light trapped within gravitationally bound systems, like galaxy clusters, will remain visible to their inhabitants. The rest will have slipped over the cosmological horizon. Their light, stretched beyond recognition, will no longer arrive. And then, after unimaginable durations, even the stars will go out. Fusion will cease. The last red dwarfs will flicker and fade. Planets will darken. The universe will enter a long twilight of glowing embers and drifting remnants. But even then, there will still be light, soft, infrared light from cooling objects, from the decay of particles, from the rare collisions of remnants. That light too will travel outward, obeying the same speed limit, the same rules. But with no eyes to see it, no instruments to catch it, its message will go unread. Still, it will travel. There's a poetic symmetry to this, that the universe began in light and may end with its fading. The first light came when the universe cooled enough to become transparent. The last light may be the final glow of a decaying particle in a darkened galaxy. Between those two extremes, light has done its work. It illuminated, it informed, it shaped stars and life and understanding. And even as it fades, it does so gently without rebellion. It never stops trying to go forward. In this context, the speed of light takes on another meaning. It's not just the fastest speed possible, it is the rhythm at which the universe breathes. It governs everything, the way particles interact, the way time flows, the way cause leads to effect. It's embedded in the equations that define the cosmos. Change the speed of light, and you unravel the coherence of physics itself. It is not just fast, it is fundamental. But for us here and now, in this narrow window of cosmic time, when stars still burn and galaxies still shine, light is everywhere. It's in the sky, in our homes, in our technology, in our cells. Photosynthesis runs on it. Sight depends on it. Communication, measurement, energy, all of these dance to the tempo of photons. We live in the golden age of light when the sky is rich with signals and the past is visible in every direction. We often take it for granted, the way light bounces, reflects, illuminates, but every glimmer, every shadow is a piece of physics playing out in real time. When you watch the sun set, you're not just watching color shift. You're watching light bend through Earth's atmosphere, stretch across curved space-time, and arrive in your eyes slightly delayed from its origin. When you look at the stars, you're reading ancient messages. When you look into another person's face, you're catching the light that has traveled a foot or two, and with it, the most immediate kind of information the universe allows. So light doesn't vanish into silence because it fails. It does so because it gives everything it has. It travels until it can't. It stretches until it fades, and even then it leaves traces, warmth, momentum, memory. In that way, every photon is a legacy, a traveler that took the only path it could, at the only speed allowed, and revealed something along the way. And with that legacy comes one final question, soft and waiting. If light carries everything we know about the universe, what lies in the places it cannot yet reach? The places light cannot yet reach are not empty. They are not voids in the traditional sense. They are parts of the universe still beyond the reach of our knowledge, not because they are hidden by dust or shadow, but because time itself has not permitted their light to arrive. They lie outside our observable universe, beyond the cosmic horizon, expanding away faster than light can close the gap. We know they exist because the laws of physics don't stop at the edge of what we can see. The universe has no known border, no enclosing shell, just a horizon drawn by time and the speed of light, a limit to how far signals have had the chance to travel since the beginning. These unreachable places are a kind of mirror reflecting not what is, but what could be. We assume that galaxies continue beyond the edge, that stars shine there as they do here, that the same structures repeat. And yet we can't confirm it. No photon from those realms has ever reached us, and if the expansion continues as expected, perhaps none ever will. It's a strange kind of ignorance, informed, structured, logical, but unprovable. We map the unseen using light's silence just as much as we do with its presence. And this silence, far from being a failure of understanding, is part of what makes the universe intelligible. If light were infinitely fast, there would be no horizon. Every place would be visible at once. Every change would be felt instantly. Causality would collapse, simultaneity would rule, and reality would blur. It's the limitation, the finite, constant speed of light, that keeps knowledge coherent, that allows discovery to unfold in order, that gives each observer a personal sky. Without that boundary, the very notion of distance loses meaning. What lies beyond the observable universe may be more of the same, stars, dust, gravity, or it may be different in ways we can't guess. The curvature of space, the topology of the cosmos, the deeper nature of dark energy, all of these questions linger at the edge of our visible domain. But we don't despair at the limit. We work with it. We build models that extend beyond, using the patterns we do see to predict what lies just out of view. Light hasn't yet reached us from those places, but its absence helps define the shape of our cosmic neighborhood. And within that visible sphere, what we do see is astonishing. A cosmos with hundreds of billions of galaxies, each with billions of stars, all moving, evolving, colliding, radiating. Photons stream from every direction, carrying the glow of hydrogen clouds, the pulse of pulsars, the flares of variable stars. Every bit of that light has traveled for millions or billions of years to reach us, a symphony of long journeys converging in our present. And yet, that present is fleeting. The moment you look up, those photons complete their path. They are absorbed, interpreted, and vanish into the history of experience. There is something delicate in that moment, that light, after such a long journey, finds a destination. It doesn't know it's been seen. It doesn't choose a target. But when it enters a telescope, a sensor, a human eye, it ceases to be a traveler and becomes a memory. The past turned present, information turned awareness. It's as if the universe has spent billions of years whispering a story, and we, just now, just here, have begun to listen. And yet, even within the realm light can touch, there are other kinds of boundaries. Black holes, as we've seen, trap light. Dense clouds of dust obscure stars in formation. Some regions are so energetic that light is constantly scattered and reshaped before it escapes. These too are zones of silence, places where the message is garbled or delayed, and we've learned to listen around them, to use different wavelengths, to shift from visible light to radio, to X-rays, to infrared, depending on what the situation demands. Light comes in many forms, and each unlocks a different part of the universe's story. There's radio light, long and slow, that drifts from pulsars and jets. There's ultraviolet light, sharp and energetic, revealing hot young stars. There's gamma radiation, born from the universe's most violent events. Each photon tells a version of the truth, and by gathering them all, we form a mosaic of meaning. Light's diversity is its strength. Its unchanging speed is its consistency. Together, these qualities make it our most faithful instrument. So what lies beyond light's reach today may not remain beyond it forever. As time passes, the horizon grows. More photons have time to arrive. The observable universe expands. What is dark now may shine later. Light is a wave, yes, but it is also a tide. It reaches new shores with every passing moment. And though some galaxies are slipping away due to expansion, others that were once too faint may rise into view as our instruments sharpen. The boundary between known and unknown is not fixed. It breathes with time. And what about the limit in the other direction? What lies not beyond the horizon, but before the beginning? Before the first light, before the cosmic microwave background. We cannot use photons to see there. That epoch was opaque to light. But perhaps other messengers can reach us. Gravitational waves, neutrinos, theoretical particles unbound by the same constraints. The frontier of knowledge is not a wall. It's a slope, and we climb it slowly with care, guided by what light allows and limited only by what it cannot yet carry. And in this balance, between light's power and light's limit, we find the shape of the knowable world. We find science. We find awe. We find the recognition that we are not separate from the cosmos, but part of its unfolding, made of atoms that once emitted light, bathed in photons that left their stars before our species began, bound in every sense to the rules that light obeys. So perhaps the better question isn't what lies where light cannot reach, but what it means that so much has already arrived. It means we are part of something vast and continuous, something that began long before us and will continue long after. The photons that touch our eyes tonight are survivors of unimaginable journeys. They have passed through interstellar space, through collisions and expansions, through the shifting architecture of time itself. Each one, arriving here, is a kind of miracle, not in a supernatural sense, but in the quiet statistical improbability of its path. Light rarely travels in straight lines forever. It's scattered, absorbed, redshifted, lost to expansion. And yet many still arrive. They bring with them the stories of stars, the shapes of galaxies, the echoes of beginnings. That we can intercept them at all, that we can measure, interpret, and understand them, speaks not just to our tools, but to our place in this web of existence. For what else is our mind, our brain, but a complex receiver of light? Our eyes evolved to detect the visible band of electromagnetic radiation, the same band where the sun emits most of its energy, the same range in which our world glows. It's no coincidence. We are tuned, physically and biologically, to the rhythms of light. And beyond that, we've learned to reach outside our senses, to build instruments that see in wavelengths our bodies cannot. Telescopes that gather microwaves, X-rays, radio waves, all of it light, all of it moving at the same speed, all of it telling us what lies beyond the veil. And so light becomes not just information, but connection. It links us to places we will never visit, to galaxies whose stars are too far to ever reach, whose light took billions of years to get here, and whose current state, in this very moment, may be forever unknowable. We will never know what those galaxies look like now. We can only see what they were, and yet we feel close to them. We give them names. We study their structures. We measure their velocities. We make them part of our map. This strange intimacy with the distant, this closeness with the ancient, is one of light's gifts. It allows a mind on a small blue planet to reach out, not physically, but perceptually, across the entire visible universe, to think about stars that died before Earth formed, to witness collisions that warped space and time before any human eye existed, to see not only the now, but the then, layered, textured, visible from every direction. This is not merely vision, it is presence. And when we send light out into space, a pulse of radio, a coded message, a golden record on a probe, we are participating in the same process. We are releasing photons into the dark, hoping they might one day find another eye, another sensor, another intelligence. We don't know if anyone is listening, but we send the light anyway, because light is how we say, we were here. This was our voice. This was our thought. This was our place in the timeline. That's what makes light a messenger not only of stars and physics, but of ourselves. Every photograph is a moment trapped in light. Every memory of a face is encoded in the photons that bounced from skin to eye to brain. Our world is shaped not only by what light shows us, but by how we use it to reach each other. Communication, expression, art, science, they all depend on this shared agreement that light will carry the message and that we will interpret it with care. And through this interpretation, we find order. We measure the redshift of galaxies and chart the universe's expansion. We calculate the angles of gravitational lensing and infer the presence of dark matter. We study the flickering light of variable stars and determine their distances. We read the background radiation and reconstruct the early universe. Each time, light gives us more than beauty. It gives us clarity, the sharp edge of understanding, the data that becomes theory, and the theory that becomes prediction. And still, for all it reveals, light remains a mystery. It behaves like a wave and also like a particle. It interferes, diffracts, polarizes, yet also arrives in quantized packets. It is massless, yet carries energy and momentum. It moves through a vacuum, yet is affected by the medium. It obeys laws that are precise and consistent, yet resists any single final metaphor. Even the act of measuring light, detecting a photon, can collapse its wave function, changing its outcome. Light not only shows us reality, it reacts to our questions about it. And in this delicate dance between the known and the unknowable, we find something human. We are made of atoms, forged in the hearts of stars, and we are illuminated by the same kind of photons those stars shed. We are shaped by light and seekers of it. We live in its presence and depend on its constancy. And though we cannot move at its speed, we can think at its pace. Our minds can follow its logic, trace its paths, measure its rhythms. And in doing so, we find our place in the great unfolding. So when we say that light is a constant, we mean it in every sense. Constant in speed, constant in behavior, constant in the shaping of time and knowledge. It is the unbroken line through an ever-changing universe. It is what binds the past to the present, the distant to the near, the seen to the unseen. And in that binding, it reveals a cosmos that is not random, but structured, not silent, but singing. And still, even as we understand all of this, light remains gentle. It does not demand attention. It does not rush. It simply moves, steadily and clearly, always at the same speed. Whether across a room or across a billion light years, it obeys the same law, the same tempo, the same invisible thread. And if you pause just for a moment and close your eyes, you can still feel it. The warmth of it, the presence of it, the glow of a universe that without saying a word tells you everything it knows. And somewhere, far away, farther than our minds can comfortably hold, a photon begins its journey. It escapes the surface of a dying star, squeezed out in the last burst of light before collapse. Or maybe it slips from the swirling edge of a galaxy, flung outward by the motion of countless stars. Or perhaps it's born from the cold glow of hydrogen collapsing, a signal of something just beginning. Wherever it begins, it sets out across space at the only pace allowed, not fast, not slow, just exactly what the universe permits. It doesn't pause, it doesn't choose, it travels, unwavering, through the vast, expanding dark. It may travel for 100 million years before it finds anything, or 1 billion. It might cross entire voids where no galaxies dwell, regions of pure silence except for the occasional glimmer of cosmic microwave background, the cooled memory of the universe's first breath. And still it continues. Maybe it brushes near a cluster of galaxies and is slightly bent by their gravity, its path nudged without ever stopping. Maybe it passes through the faint haze of intergalactic gas, losing a little energy, stretching just a bit more. But it does not end. Eventually, perhaps after 10 billion years, or maybe just 1,000, it encounters something. An eye, a lens, a sensor, a mirror. It is absorbed, transformed into heat, or electricity, or an image, Its journey ends not with an explosion, but with a whisper. Its information, the encoded signature of its birth, is finally received. That photon's trip, which spanned a third of the age of the universe, concludes in a blink, a trace on a screen, a shimmer on a detector, and it will never happen again. Multiply that by countless trillions, photons arriving every instant from every direction, each with its own origin story. Some are fresh, from nearby stars, from our own sun, from light bulbs and candles. Others are ancient, older than Earth, older than the very atoms in our bodies. And yet, for all their variety, they all obey the same rule. They all move at the speed of light. They all travel at the rate that links time to space and binds every moment to the next. This quiet constancy, this perfect speed, defines everything. Without it, time would lose coherence, distance would lose shape, causality would become untrustworthy. The speed of light is not just the maximum speed, it is the governing rule of how reality connects with itself. It is the speed of now turning into later, the rate at which one place can know another, the pulse that underlies everything that happens, everywhere, and it remains, even as stars burn out and galaxies collide and space itself stretches thin, even as the night sky gradually empties and the oldest light fades into darkness. Even as entropy rises and time marches forward, this one thing holds. Light always moves the same way, at the same pace, through every inch of the universe. It is the thread that will remain when everything else has changed. In the deepest future, when the last stars have died and the last black holes have evaporated, when the universe is cold and silent and scattered, light will still echo in the dark. A faint radiation, a whisper of warmth. And though it may no longer illuminate worlds or stir minds, it will still mark time, the same old pace, the same connection between here and there, between then and now. That is how the universe remembers itself, not through grand declarations, but through the travel of light across time, through signals sent and eventually received, through photons that do not experience time, yet carry it, that do not age, yet tell the stories of aging, that are massless, yet move the mass of minds. And we, who observe, who reflect, who measure, are part of this quiet pattern. We are creatures of starlight, born into a world where light already traveled. Our skin feels its warmth. Our eyes read its patterns. Our thoughts arise because light has moved and reached and arrived. Everything we know, every equation, every memory, every dream, is shaped by what light has shown us. So let it continue. Let light stretch across the vastness. Let it bend around gravity, pass through clouds, fade into microwave, travel to the edge of time. Let it reach new observers in distant futures, different eyes, different ways of seeing. Because light is not just how we understand the universe, it is how the universe understands itself. And here, as your eyes close and your breath settles, remember, above you and around you, photons are still arriving. They've been traveling for ages, and now they are here, quiet messengers from elsewhere, still faithful to the rules of time and space, gentle and constant, slipping through darkness, delivering their stories in silence. And somewhere, just beginning, a new one sets out at the only speed the universe will allow.